Okay, for problem number 21 here, this is going back to our model. So if I plot energy along this, so if I have N is equal to 1, N is equal to 2, N is equal to 3, and I can keep going up here until I get to N is equal to infinity minus 1. That's the last bound state. As soon as I make the electron go into N equals infinity, that means it's a free electron. And that's what you want to calculate. What's the energy required to do that? So we have to know the energies of these states, and that comes from the book. It's the Rydberg constant, R, times 1 over N squared, and this would be for 1. This would be R times 1 over N squared for N is equal to 2, and so on, up to R times 1 over infinity squared. And then to calculate the delta E, because this is really what this wants, the change in the energy going from the electron in this level up to that infinity, it's going to be equal to just the difference in those levels. So we're going to take R times 1 over N equals 1, that whole thing squared, minus R times 1 over infinity, that whole thing squared. So it's equal to R times 1 squared minus 1 over infinity squared. And the question is, what is 1 over infinity? Well, as this number here gets larger and larger and larger, this number, this fraction, so that's a parenthesis around there, that fraction gets smaller and smaller. So 1 over infinity approaches 0. So this becomes just simply equal to R. Now the question is sign. We could keep track of the signs here carefully, but it's better just to think about what delta E means. Are we putting energy into a system? That's a delta E, that's we're adding energy. If energy is coming out, if photons are given out, then that's minus E, energy is coming out. So this is energy going in, it's equal to R, and the value of R is 2.18 times 10 to the minus 18th joules. You can look that in your book. So the correct answer is going to be a positive 2.18 times 10 to the minus 18. Now this is a pretty straightforward question, number 22 here, if you understand this way this works. So we've got our nucleus, and then we've got N is equal to 1, we've got N is equal to 2, and then we've got N is equal to 3. And remember, we start only with S's, and then every time we go out a shell, S and P's, we add. So out here we've got S, P's, and we've got D's. So every time we go out, we add. Or you can look at it this way. N is equal to 3, L is equal to N minus 1, and then the value of that can go down to 0 at integer values. So if we start with 3 minus 1 equal to 2, we can have 1, we can have 0. That is S, P, and D orbitals. So the answer there is going to be that. For question number 23, we just need to simply look at which one of these sets of quantum numbers are not. This is choose the one set of quantum numbers that does not contain an error. So these are all going to contain errors except one. So we just start at the top and work our way down in a multiple choice question. And so we start with N equals 5, so we can have L equal to 4 down to 0. That's okay. And L can be, M sub L can be 3 to minus 3. So that's actually okay. That does not contain an error as far as I can see. And then we've got 4, and if we've got L is equal to 0, that's allowed. But L can only be then, M sub L can only be 0, and that's not. So that's wrong. Here we've got 3, L is okay, L equals 1, but we can only go from 1, 0, minus 1, so that's wrong. 3, L is equal to 2, that's okay, but we can't have an M sub L that's greater than L, so that's wrong. And then we have N equals 4, L equals 4, well, N minus 1 is equal to L, so that's wrong. So the only one that does not contain an error is that one.